Okay, we have a dense lecture today, and it's stuff that you can use for not just classical mechanics, but quantum mechanics as well. And that will be true of the next lecture, where we make a connection between the two that's very solid. The thing I want to do today mostly is do the algebra of solving an eigenvalue problem in an elegant way. And we have to do that in order to study the motion of 2, 3, 4, 5 coupled oscillators. So the picture sort of changes now from the situation where we had an infinite force that applied its resonance to a single object. We could have that too, but here all of these will be autonomous, that is, without outside influence. But in order to do that, we need to find the eigenvectors of the matrices, define those matrices, that define the acceleration, force, and all of that of the devices that we're working with here. Which is just this guy right here on the overhead projector is the best mechanical one that I've been able to come up with. We do need to find a way to make really good bearings, but the idea of a coupled pendulum is what that one is. We'll be solving problems that are like this, and that's the homework problem I've given you. That is the third problem on today's assignment. Now, the equations for these things, the Lagrange equations, are very simple. No problem getting the Lagrange force equation. If you want to have a potential, be my guest, and that potential will be given by Hooke's laws, basically, the energy associated with spring K1 plus the energy associated with moving this K2, and then the difference between these two with another spring, K12. So that potential is a quadratic form, and we're going to make use of that in a number of ways, geometric and as well as algebraic. In any case, this is the Lagrange equation expressed by matrix. The matrix having diagonal terms which correspond to the products, the coefficients of the x1 and x2 individual, and then the coupling. We end up with two of these, so the canceling of 1/2 occurs, and the matrix is very simple. So that's what we have to deal with as far as now we're going to use Dirac notation. It's perfectly okay to do that, right? And in fact, we're going to make a connection in the next lecture to Schrodinger equations. But we've got enough to deal with here for the time being. So here is the quadratic form expressed in terms of Ketzen-Braz. And there is a section in the Unit 4 chapter that goes through a real quick review of using Braz and Ketz for classical objects. In any case, there's a lot of symmetry and things like that we won't talk about. The idea of having a reciprocity relation so that the two spring constants off diagonal are equal to each other. That's just another example of the derivatives commuting. And that's really kind of a neat demonstration, which I don't have time for. Basic ideas: if you have any system and you push on one part of it and look how the other one moves, and then apply the same force to that one, this one will move the same. And that looks a little bit mysterious when you think about it, but this is making it look very obvious. Then if you're going to be doing molecular physics and you have a lot of masses that you have to worry about, you can rescale it so they go away. It makes the problem more like what we're going to be dealing with today, which is equal inertias, equal masses. So we keep the kinetic term in a unit form. So this is what we're really going to be dealing with right here. When I divide through by the masses, I get a matrix there that is not symmetric. And the previous slide is a way to get around that, but you have to watch out. You get some really weird stuff sometimes when you do that. In any case, this is the order of the day right here, is to find out what are the eigenvectors of this particular acceleration operator. This is a Riemann equation now. The acceleration is exposed on the left-hand side of the equation, and everything else is on the right-hand side. And we're into simply here an eigenvalue problem. Now, be aware that most of the information, certainly in large problems, which you're going to be encountering in your research, most of the information is in the eigenvectors. Eigenvalues, there's n of those. There's n squared numbers associated with the eigenvalues, because there's n eigenvectors and each one of them has n components. So that's where the physics information is, and so getting that is important, very important. Eigenvalues are cheap, eigenvectors are not. So the idea here is to figure out an elegant way to deal with eigenvectors. So we're going to introduce that whole business here just with unit masses, and everything will be spring constants in the K matrix. And basic idea is, what's the geometry of all of this? So I'm going to come forward here and get those pictures up. And the picture I have in mind is the quadratic form. But now it's a quadratic form in coordinates, not in momentum. We started this whole course with quadratic forms involving momentum and velocity, Hamiltonian or Lagrangian. Now we've got the driver for something like this system. And the driver consists of a K matrix. And that K matrix has a plot of, well, you guessed it, if all of these are positive constants, it's an ellipse. And this particular ellipse is rather special in the sense that its axes are tipped by exactly 45 degrees. That's the symmetry. That's coming about here when we adjust the constants for the K matrix in such that it gives that. So we're going to be making, for the first go-around here, we're going to be making K1 and K2 equal in the demonstrations that we show of this to start. In any case, the real question then is, what direction x, and that's going to be an eigenvector if we can pull this off, has the same direction as the K matrix times that vector. So what, if any, direction satisfies this? And you can see pretty easily by looking at the geometry of these things that most directions don't satisfy that. There's a continuous infinity of directions that don't satisfy that. There are just some very special directions that satisfy this equation being equal to or in the same direction as dx. Okay, so remember how you handle a quadratic form, figuring out where directions of things are. If this is the vector x, then the vector kx is perpendicular to a tangent to that point. Remember that? We used that as we discussed the Lagrangian versus Hamiltonian and all that geometry. Well, here we're using it again. It's pretty obvious now if you think of it in terms of force, because what you're talking about is the physicist's force, and mathematician's force is this one right here, to hold the thing on the slope, so to speak, of the potential gradients associated with the quadratic form. And if I let it go, I'm going to take off in this direction to start with. Then I'm going to go all over the place. But this is the basic idea. So this is the fall line of a ski resort that I call Bear Valley, B-A-R-E. Okay. There's a Bear Valley in California, but it's B-E-A-R. This is a Bear Resort. It has a beginner slope and an advanced slope, and that's it. The rest of the slopes here are complicated like that. Okay, so that's basically the geometry that we're working with here. The mass times the acceleration, if they were matrixing vector respectively, is equal to minus k dot x, but we're just going to work with k dot x because we have masses equal. It's one mass going around in this thing. So what we're dealing with here then by geometry, it's a very obvious situation. We can see right away that this right here is a very nice eigenvector. That's the beginner slope. It's going to be nice and gentle. You can see the topography lines are quite a bit between each other, whereas over here they're a little they're squeezed together more. And so this is going to have a lot more frequency than this for the actual motion. Well, maybe not a lot more, because this isn't really a very eccentric ellipse that I've taken, but it's enough to make a difference. So that's what we're dealing with as far as the geometry associated with this. Now very quickly I can go ahead here and just do a simulation of this thing, and the simulation is a heck of a lot better than the actual demonstrations that we'll be doing later. But let's just get a picture of this going here. So here is a typical motion. It's all over the place. You back and forth in Bear Valley, going up and down and sideways and everything. But if I can start off on the beginner slope, which is right there, it's really simple. So there's an eigenmotion right there. There's a normal mode is what it's called. And it is normal in the sense that it's normal, that's perpendicular to the advanced slope here. The advanced slope, which you can see is a little bit faster. And I didn't quite get it on there, so it's making a little ellipse or something like that. It's not an ellipse because we have some funny numbers describing the actual frequencies, the eigenvalues. So those are all things that we're going to be getting. We're trying to get an elegant piece of algebra and geometry. Now we're going to turn to the algebra. Okay, so pause that. Go back to the workshop here and continue with what we need to do. So to do this mathematics of eigensolutions, I have picked an example which is a little bit meaner than the examples that you'll be getting in quantum mechanics. And every one of your quantum mechanical problems that are associated with pure quantum mechanics and not outside influences, the density matrix and things like that, but every one of them has a symmetric matrix, basically, if it's real, a Hermitian matrix if it's not. Okay, so you have these hoity-toity matrices in quantum mechanics, but this one right here is the first example of when it's not hoity-toity. It's not a symmetric, so how do we handle eigensolutions with something that's a little off-kilter? That's why I picked this matrix. Also, it's easy to remember, 1, 2, 3, 4, and it gives us integer eigenvalues. So this is a good one to work with. But of course, you're going to be working with much larger ones as you do your research if you're a theorist. Now, the question is, how do we find what the eigenvalue of this is? In other words, how do we find, and I said the eigenvectors are more important, how do we find x and y for this thing? And how's the deal here? So solving a linear equation, okay, and I say it's a fool's errand now for the linear equation, because if I use Cramer's inversion, the Cramer's inversion amounts to taking a determinant of the original matrix and then substituting for each column, first column for the x, second column for the y, the inhomogeneous part of that equation, namely 0, 0. And it's a fool's errand because the answer for x and y is 0 for both. So if you take your first job, and your first job is to find the eigenvectors of this matrix, as you go off, and you come back to the boss and say, I got it, it's 0 and 0. They're going to pay you, right? You're fired. We got to fix this. Okay, how do we fix this? All right, well, the only possible non-zero x and y is if this thing is 0 also. I got to have an indeterminate form to pull this off, okay, and keep me from getting fired. Okay, very simple. All right, so I'm going to go ahead and take that determinant. Okay, and it's just minus epsilon times the unit matrix, this thing right here. I'm just going to write this whole equation on one side here, and say the determinant has to be 0. That is called the secular equation. These names come from the government that involved Catholic Church. So the secular stuff was very questionable. You had to be priestly or churchy in those days. Okay, or the Inquisition would come and get you. So this is, I find it amusing. We talk about the secular equation. But that's what it is. And it's an easy equation to get, particularly here for 2 by 2, because when I put this together here, when I actually take this determinant, 4 minus epsilon, 2 minus epsilon, times 2 minus epsilon, minus 1 times 3, that's the determinant now, and collect the terms, I get epsilon squared here minus 6 epsilon plus 5. I could have done that really quickly because the first term in the n by 1, this one right here, is always minus the trace of the matrix. So I just have to sum up the diagonal. Okay? And then every other term is a sum of diagonal k by k minors. The kth term, you have to learn how to do that. And then finally, the very last term, this one right here, is simply minus 1 to, well, in this case, 2, so there's no minus, the determinant of this matrix, 1, 2, 3, 4. So the last one is 4 times 2 is 8, minus 3 times 1 is 5. That's this number right there, okay? That's cool. That's an equation that's pretty easy to solve. And when you do it, when you factor it, you discover that your eigenvalues are 1 and 5. So that's what we'll call epsilon 1 and epsilon 2. Okay? Over here, solving this is going to be an nth order equation. Okay? You have an nth degree polynomial to deal with for an n by n matrix. So that's not trivial, but it's very understandable, and we know a lot about polynomials, and that's what we're going to make use of here. So, basic idea is these n factors, one for each eigenvalue, can be replaced, that is, the epsilon can be replaced by the matrix itself. Now this is called the Hamilton-Cayley theorem. And I'm saying it's really obviously true if M is capable of being reduced to diagonal form. But that's circular logic. That's something that would be very obvious if M was one of your hoity-toity matrices. You can prove this very easily for that one. But we're doing general matrices here, so we not going to use circular logic. We're just not going to prove this. This takes a long time. I challenge you to find a short proof that I could use in a class that wouldn't waste a lot of time. So you come up with that, and you've got, I'll up you 1 grade, for sure. Okay, so here is the matrix that we have, 1, 2, 3, 4 squared, and then 6 times it, and then the unit thing. That's the other thing you have to do, is you have to replace the epsilon eigenvalues with a unit operator. But we put that together, sum it all up, and bingo, we get a 0 matrix. That's what this is telling us. So that's cool. This is really an incredible thing. And Hamilton's name on this, his name is on everything we do for the rest of this course. Okay, so be aware of this particular thing. Now, once we've got this, once we've realized that this equation here with n factors is a 0 matrix, we can start playing with that. We can say, okay, if that's 0, what's it like if I take one of these factors away? Well, there's only 2 factors, so maybe the first one that I would take away would be the one that has the eigenvalue 1. So I'd be left with a unit operator times n minus 5. That turns out to be a projector that contains both the Ketz and the Bra eigenvectors. They're not normalized yet, but those columns there are eigenkets, and those rows there are eigenbras. And the Ketz and the Bras are not the same, and they're not simply complex conjugates of each other like they are in quantum mechanics. Remember, this is not a hoity-toity matrix. So this is how we handle non-hoity-toity matrices. we're on the way to making a rediscovery of bras and kets for matrices in general. That's what's coming out of this. Okay? So that's what we do with the N1 here. We take the first factor out, take the second factor out, and so on, all the way down the row here, and we get a bunch of little projectors, is what they're. Projectors haven't been normalized yet, so I use lowercase p for them. But in the next few go-arounds here, we're going to fix that. Okay, so here's where we stand. We've got here this, and I'll put this one forward too. Definitely see that when I multiply our matrix M, 1, 2, 3, 4, by this projector, I get the projector back against times the eigenvalue. I literally get it back again without any change. So this is an eigenoperator, first one. This is another eigenoperator, okay, this one right here. But it gives eigenvalue 5. Okay, so this is cool. Now we're working all with operators and not having to actually fiddle with the vectors. That's powerful. Okay, so the idea is that these are eigenbrackets, or ket bras, depending on how we look at it. We'll do that in a minute here. But also, you should notice, and this is important, and I'll put it on both slides here, these little p's here commute with M. They're structured things, but they have to commute with M because M commutes with M and every power of M. And that's what they're made of. They're made of the combinations of powers of M in general, and they will therefore always commute. So that's proving that we can get both the kets and the bras. I should say kets and bras if I'm looking at it from this side. Okay, so that's what we're at. That's what's going to happen now, is we're going to take advantage of all of this. And it all comes from this guy. Okay, so now just a question. How many people have seen this already? Anybody? This structure. I mean, that's a terrible thing. That's absolutely terrible. But you came to the right room. Okay, because we're going to make use of this. We're going to get orthonormality completeness, all kinds of things, spectral decompositions. Man, this is powerful. Okay, that's what you get for being a little careful with your algebra. Okay, let's get both of these guys running the same here. I want to normalize this sucker. These little p's here, when I multiply them together, in general I get the little p and then the other one, and the idea of course is that this is a product, this p little k here is a product of m minus eigenvalue m for all m. We only have one for the 2 by 2, but for 3 by 3 you'd have 2, all m except k, all except k, okay? Now if I put the k back in this thing, this is going to become 0, because that's the entire Hamilton-Cayley equation, which always gives you 0. So I go in there and I see pj multiplying the m. Well, I know what that is. That's just going to give me eigenvalue epsilon j times p, and then there's the general situation here. And the basic idea is that when I multiply these two operators together, if j is not equal to k, I'm out of here because I'm going to recreate the Hamilton-Cayley equation, which gives me a big fat matrix 0. Okay, so j is not equal to k, I'm definitely going to get a 0. But if j is equal to k, okay, now I get something that depends on the difference between two eigenvalues. All of them am not equal to k. Not equal to k, so this is not 0. Well, it's not 0 if the matrix doesn't have degeneracy. If it has some symmetry that makes some degeneracy, ooh, look out. We're going to do that in another lecture. So everything we're going to deal with here on this side for the n by n is assumed to not be degenerate, have no degenerate eigenvalues. And if you make a matrix of random numbers, you will never, ever get a matrix that has two equal eigenvalues. That's cool. So it'll never be degenerate if it's random. But if it has symmetry, look out. And that's what's really powerful about this algebra, is it has let me completely change the way you treat group theory for physics. It makes it simple, it makes it understandable. And group theory is hated by everybody in this building, as far as I can tell. Because it's really hard to read Wigner and books like that. They don't explain it.
If it is not degenerate, shouldn't the order be upside down? Like J equal to K is 0 if it's not degenerate.
K, this product, this thing right here, this product of J and K, okay, is going to be 0 if J is not equal to K, and this matrix has no degeneracy, because there is a possibility that the eigenvalues would be equal, in which case this would go to 0. It would be possible for this to go to 0. Now,
oh, right. It's
I'm not going to let it be. I'm not going to let it be.
Right, gotcha.
Yeah. I'm going to avoid that. Thank you for the question. I'm going to avoid that until another lecture. Okay. We've got a finite amount of time per lecture, so we got a lot to cover anyway. So here's the deal.
More clear.
All I have to do is divide by this sucker, which is not 0, and I get the big P's, and those are the ones I want. Those are the ones that are really going to swing for us. So we definitely want these guys to be normalized in this fashion by these weird product of all of the differences, of K minus M, except M equal to K, right? Well, in our case, we have no problem with that, because we don't have any possibility of degeneracy with a 2 by 2 like this. It's got 1 and 5, and that's it. So I get this, and then I get 1 minus 5 here, okay? I'm talking about a minus 4, but then I've taken that minus and put it on this matrix that has minuses on it. It doesn't have them anymore. And then with this one, I don't have to worry. 5 minus 1 is 4, and just go ahead and use that thing straight away. So there's a normalization factor for the projectors, the little p projectors, that makes them big P's, puts on the big grown-up pants, okay, ready to go to work.
What is the difference between big and small? The difference between big P and small p. What's the difference?
The difference is that normalization factor, that's all. And let me turn this off so I can hear you better. The difference between the big P and the little p's is that I have put this factor in there, which is 1/4 in this case.
Why?
5 minus 1.
Why do you need that normalization?
Oh boy, do I ever need that. Wow. Yeah. Ask that question a little bit later. Okay. We'll go ahead and do some things here. But the main thing I want is the product of this thing here to be a delta function. Delta K. That's the first reason. I want my orthonormality to work, not just be orthogonality. I want it to be orthonormality. Okay, now I'll explain all that later in just a bit here. Okay, but that is a good question, and we want this. We want these guys to be not impotent, just the opposite of that, idempotent. Okay, idempotent means that you've got something when multiplied by itself gives back a self. Now, unit operator does that very nicely, thank you, but these are more complicated than unit operators. So all of these p's we're going to get here, no matter what the degeneracy, after we place an extra trick, is got to be an idempotent operator. That is, this operator times itself is itself, and this one is 2. But this one times that one, absolutely 0, because you just recreated the Hamilton-Cayley polynomial and it's 0. So here's where orthonormality comes from in a mathematical sense. Hamilton-Cayley equation, theorem. Okay, cool, cool. We can live with it. Okay, so it's true we already have a set of little p's that give us eigenoperators, but I want them normalized. okay? And just to again answer your question, I want them to be normalized, and we'll see why quite soon. Because there's more to orthonormality. There's the other side of orthonormality is called completeness, and we need that real bad. Okay, so that's what we're getting to here, right here. Okay, we already got this solved, but what about that one? That's the one that really is magic. But here's what we can do with what we've got so far. I can simply look at that P1, big P1 now, which I'm really trusting as far as orthonormality goes. And I can look in there and I can factor this sucker into an outer product of a ket and a bra. So when I get done multiplying these things, I can do it by putting any factor I want on this one as long as I divide when I go to the bra. So I call this gauge scale factors. They don't affect the algebra, but they do affect the drawings of these things that we're going to put in here very strongly, obviously. They make them bigger or smaller depending on what the K is. Okay? So anyway, what I want is 1/2 times 1/2 to be 1/4. I want 1/2 times minus 1/2 to be minus 1/4. And then this guy right here, that's got to be 3/4 with a minus sign. And then this thing times that thing is a plus 3/4. Okay, so very quickly I can factor this thing into a ket and a bra, and then I can scale them any way I want. So here's a picture in Dirac's notation of what it is that the big P's are. They're ket bras. They're matrices. Okay? And here's the other one. The one that's orthogonal to this one is made the same way. I just factor this thing, and I can factor it many different ways because I can put a K1 up and down on this one, and I can put a different K up and down on this one. So I can make these real small and these real big, or I can make them all equal. Make a long story short, here's what I just made. Okay, so let's get that up on both screens here. Okay, let's look at a couple of these guys that we have here so far. P1 is a 1 minus 3. Okay, that's if it's a ket. The ket, E1, there is a 1 minus 3. Well, it's 1 minus 3 over 2. Okay, I'm looking at the ket right here. 1/2 minus 3/2. But I ought to look at the bra while I'm at it. There's the bra right there. Okay? That's ket 1. There's bra 1. Bra 1 is that guy. 1/2 minus 1/2. And you'll see they don't line up with each other. One of them is contravariant and the other one's covariant, right? Well, maybe not right, but it looks like that. And it will turn out to be that. And here's E2, okay? This guy gives me right off the bat the ket 1/2, 1/2. That's this guy right here. Oh, and times K2. I can put any factor on this one as long as I divide that factor to this one, which is that guy, 3/2, 1/2. Okay, is this making sense? Yeah, I agree. If I'm seeing this for the first time, I've got to stop. Stop. I got to go read it. I got to do something. Go drink coffee, which I don't drink. Okay, so this is what's going on. We're creating the dual space. This is a most elementary dual space that I can show you that really works for physics. So this is the matrix that started it all. These are the projectors that make it. Okay, there's the outer product of the vectors that are giving this particular ket bra. That's the 1, 1. And then the 2, 2 is over there. So those are the diagonal parts of this story. But then we have little crosses for the other ones too. We'll get into that later on. So This is where this gets very powerful.
Excuse
Okay.
me.
So let me pause for a second here.
How do you get from the matrix
This guy.
to that bracket?
Okay. As I say, and thank you for
it's,
asking.
It's for
Tricky step.
unknown. Yeah, it is.
I mean, I could have a much bigger matrix here, 3 by 3. I'd be doing the same thing. But I have, you see, a lot of choices. I could pick this guy to go with this guy, or I could pick this guy to go with that guy. Or I could pick this guy to go with that guy. Either way, okay, I'm going to factor them in some convenient way. So I have to have a 4 here. If I had a 5, I'd have some radicals up here. I literally tear this number apart 1/4 and put part of it here and part of it there. As long as what I'm getting here matches with a row, I can take column. But then I could take this column if I wanted to. That would be equivalent of changing the numbers here, the gauge scale. So there's hidden behind the scenes here a lot of different choices. But this is the only projector in town for number 1 eigenvalue. And this is the only projector in town for the number 2. But if you want to go and talk to people that like Dirac, who have bras and kits, well, this is what you have to do to make them happy. Does that help at all?
So is this unitary? I mean, is there a general lemma or trick that
to handle the tricky step, it's whatever works. So I could put all of the 1/4 here and then have a 1 right there. But I pay the price of having something different as I kept doing that. You see. So there's, behind the scenes, a lot of loosey-goosey, but this is solid. This has not changed. You see, this is solid rock stand. Those are the fluffy things. That's why it makes quantum mechanics so hard, because there are all those things in there that you don't have a solid way to handle.
But this is not a unique solution.
Yeah, that's
Say again?
what I asked. Are E1, E2, epsilon 1 or 2 are unitary, unique, or it's just a random basis?
If your matrix is Hermitian, all of these will be Hermitian. And that'll make your factoring a lot simpler. And there won't be a difference really in numbers for the bras and the kets. They'll just be conjugates of each other. Transpose conjugates. You see. We don't have to, we get that automatically now if you want it. But this is not Hermitian matrix, so we don't automatically get projection operators that are perfectly Hermitian, because the thing that made them wasn't. Okay, does that help a little bit? All right, let's keep going, because completeness, this is absolutely amazing. I mean, it's not amazing when you talk about wave mechanics and stuff like that, but mathematically, this is really quite thing. Now, as we said, the PJ are mutually orthonormal. We've said that a number of times. As our bra ket, these guys right here come together, epsilon bra times epsilon number 1 ket, okay, that's got to be 1. We've normalized, so the vectors automatically obey our normalization. This guy right here is 0, this guy right here is absolutely 0. That's orthogonality. That will be there in every case that you do this stuff. And so we got a nice 1 there. The thing that is, the orthogonality is pretty easy to see, because all that's doing is recreating the Hamilton, Cayley. I keep forgetting poor old Mr. Cayley. He was an excellent algebraist, and many years after Hamilton. Okay, he just comes back and makes this stuff. But what a magical trick it is that the sum of these projectors, the sum of these two guys, is the unit matrix. Whoa! How did that come about? we gotta prove that. But we're not gonna do it right away. We're just gonna see that it is definitely true for the 1, 2, 3, 4 matrix. Just add those two suckers right there, and what do you get? 3/4 plus 1/4 is 1. This cancels that. This cancels that, and there's 3/4 there plus 1/4 there. That's a unit matrix. Wow! Now you've got something you can play with. Now you got something you can do business with. That's the whole deal here. And it's what's called spectral decomposition. You can spectrally decompose these matrices in a beautiful way. Remember that the matrix M multiplied by one of these things, like M times P sub 1, gives you eigenvalue epsilon 1 times P1. They're still eigenoperators even though we've normalized them. That doesn't affect that. So if I take M and multiply it by 1, that's equivalent to multiplying it by P1 plus P2 plus Pn. And that gives me a linear combination now with coefficients that are eigenvalues. That is called a spectral decomposition. And you don't hear about much because most of the ways to get it are just shitty. This is a cool way to get that. And you can take it up and do it with, Banach operators in continuous space. But that's getting ahead of our story here. As you can see very clearly here, if I go 1 times P1 plus 5 times number 2, which is a 5 eigenvalue epsilon 2, and add them up, I get the matrix back. Okay, I get the whole matrix back. But we aren't done yet. We are not done yet. This is what really is powerful about that. Functional spectral decomposition. Okay? Any function of M is very easy to calculate. If you've got the P's and the eigenvalues, you simply take the function of each of the eigenvalues and multiply it by the projectors. If the function is just epsilon, then fine. That's the spectral decomposition. This is a functional spectral decomposition. Wow, is that something else? You want to do 50 powers of M? What if I said I want these matrices 50 times, and we've only got 15 minutes. I want you to get that, okay? You've got to multiply this matrix by itself 50 times. Easy, easy, easy peasy. All I got to do is go 1 to the 50th times the first projector plus 5 to the 50th times the second. I got closed form answer here for the 50th power of this matrix. Bam. That's pretty cool. And I'm going to ask you to find the square root of a matrix. Okay, but that's on your problems. You can, I'll play with that. And then you got to test it, of course. Does the square of what you get with that mess work out? Yes, it does. Let's go on here because we have to go and make connection with the ordinary ways of handling linear algebra in, quantum theory. But classical needs it too. Here we have x, y orthonormality. Okay, if we have a wave function, okay, or a state that has x's and y's and maybe a whole bunch of different values for the coordinates, okay, that give you a delta function. That's the orthonormality. But it's based on the completeness of these new vectors epsilon that we've created. And then the epsilons are orthonormal. We've shown that already. That's based on the completeness of the base x and y that we started with, the Cartesians, presumably coordinates, that gave us this matrix right here. We're going to switch to another basis, which is the epsilon 1, epsilon 2 basis. The Bras and Ketz are all sitting cattywampus there. Okay? So when you state this way, which one's the orthonormality and which one's the completeness? The answer is both of them. but not at once. One of them is orthonormal and the other is complete, depending on what basis you started with or the one you ended with. Okay, that's powerful too. But I want to really emphasize it. I mean, I want you to see that they look like just two sides of the same coin when we do this. They really show that they're both orthonormality and completeness. Okay? This is the orthonormality of the coordinates we started with, and this is the funny coordinates that are at 45 degrees, say, and the modes we're about to do today. Okay? And we're going to have this guy be orthonormal, and those guys be complete. They're going to give us a 1 when we sum up their projectors. Their Ket-Bras, okay? Represented in the old coordinate system, x and y. But we can just turn that whole thing around and get another 1 by the orthonormality of the epsilons. And then we'll have completeness for the x's and y's. So I'm saying here, quite similar representations of completeness. It's like two sides of the same coin. But, do your quantum mechanics books show this? No. They think of wave functions. This is a wave function here, psi 1 of x. Okay, the x is always sitting on the left-hand side. And then a psi star of y. Okay, now it's turned around, so you put a star on it. Okay, you sum those guys up, and you get a Dirac delta function, because if you summing them up infinitely, x and y is continuous variable, this has got to be Banach space, and you've got to have a Dirac delta function instead of an ordinary delta function. This guy down here, now you can have a Kronecker delta for this one, but when you put the quantum mechanics on that, that's weird. You go psi star psi I and j of x and y, and so on. That is, you're doing an integral of this product, okay? That's giving you orthonormality for the size in the space of x and y. Okay? So, Schrodinger wave function shows quite a difference. It does make as clean as what we have here. Well, that's because you're working with Banach space, and Banach was a really mean mathematician. But he performed a service. He figured out how to handle the continuum. And then Dirac took it from there. Okay, now, what I'd like to do, we've got some time here, I'd like to do just the last bit of mathematics and show you another trick. This trick is something that numerical analysts, people who play with computers a lot, have to do. Somebody's given you a graph of something versus, say, x, and you have the data, dot, 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 dot. And the idea is to draw a curve that goes through every one of those points. That's called interpolation, right? Now, there are lots of ways to do interpolation. This is probably the worst, but it's the easiest. This is Lagrange interpolation right here. And what you do is you make a polynomial out of product of x minus xj for all j not equal to the k piece of data that the kth point in your data set. You leave that one out, and you do the same thing here. You go data point k minus j, but you don't ever touch. You do a product over all j's except k, just like this. Okay, all j's except k. That will give you a polynomial k, and you're guaranteed that thing is going to go through the points associated with this. That is, whenever x is equal to xj, okay, I'll get nothing. Okay, I won't get anything. But I will get a contribution when I talk about p of x, the polynomial that's associated. When x comes to xk, I can pull it off. And you'll see what I mean by that in just a minute here. So these polynomials have zeros at each point x equal xj, except where x is equal to xm. And then it's 1. Pm of xm is 1. So this is just giving you a 1 right here, and there's the data The data is that at that particular point k, I have a function that is number, well, 17 and a half, or whatever that function is for that kth point. Now, what's neat about this, of course, is that it's an approximation. But L approximation becomes exact in a situation where f of x happens to be a polynomial of degree n minus 1 or less. Then this thing gives you that is exact. There is no fuzzy buzzy in between the points. You've got an equation. For example, 1 is the sum of these points. If you just had an x1, one data point, that would be a sum of 1. Okay? Well, no problem. That determines a level line. This one's going to determine a sloping line. 2 points determine a line, right? 1 point determines a level line. 2 points determine any line, except the one that's straight up and down. It might be a little bit of a problem. But then, what are you going to do at the next stop here? Well, 3 points determines a parabola. Perfectly. Okay? Pretty neat. Now, you probably noticed that our sum here, and particularly this one, the functional spectral decomposition, is just being done here, but it's just being done with simple algebra, no operators. These are all operators up here. This is just numerical. This is just getting a curve on a graph, given a bunch of points and trying to get the curve to go through it. It'll go through it. The question is what's happening in between. It's maybe total garbage, and that's why this is not used very much, because the polynomials, you know how they go crazy. So that's the thing. Anyway, all distinct values satisfy a thing that is like this. So basically what we've done here is we have proved, by using Lagrange's interpolation and looking at it carefully, we've proved that the completeness relation, the sum of all of those p's, is equal to 1. That is truer than true. By truer and true, I mean it's doing what I wouldn't have expected until I actually work it out. P1 plus P2, let's just do that one right there. Let's just sum up. P1 plus P2 gives you this, gives you that. They cancel to 1. Exact. In other words, you could put in any eigenvalues into this formula, and it'll still add up to 1. Put any numbers in there for those epsilons that are different, and it adds up to 1. So it's truer than true. The completeness projector sum is truer than true. Now, you've got to be aware, of course, that when it comes to doing the other stuff like eigenvalues, you've got to get the right eigenvalues, or that's not going to work. Or orthonormality is going to depend on you putting the right numbers in. Completeness does not depend on that. Oh, this is too much, right? I mean, what a story that hasn't been told very well. There's little pieces of it here and there. If you take a good mathematics course, you'd learn some of this, I'm sure, although I can't guarantee it at the University of Arkansas. Anyway, real quick here, I want to go through some secretarial work, and then we've got a good 20 minutes to play with the actual physics that we get. We'll have to rush through it a little bit, but I'm trying to get all of this story in one. In case I die this weekend, you've still had a good course. Okay, so here's the P1 with its other ways of writing it, and the sum of those would come out to be a nice unit operator, unit matrix actually, okay? And the question is, how do you handle the stuff that you actually do in quantum mechanics? And in other words, how do you get the D-tran, the diagonalizing transformation? You're going to have to do this sometimes to get the eigenvalues out when you're doing computational things. So you have to know how to use your projectors for that. So basically what you do is you load the distinct bras into rows and kets into, well, inverse D-tran columns, and I'll show you what that means very quickly here. So the idea here is that we've got a bunch of bras and we've got a bunch of kets. How are we going to use those to make the D-tran and the inverse D-tran? Okay, now remember, this is a matrix 1, 2, 3, 4 that is not hoity-toity. It's not Hermitian. So getting these two matrices to then diagonalize 1, 2, 3, 4 into 1, 5 diagonal. That's how you do it. Okay, that's kind of neat. Now, by the way, it doesn't matter if you have complex numbers in this matrix. I could have put an I on the 3, and this would all work. It's just to make it a little messier. But in any case, here's the matrix you started with, say 1, 2, 3, 4. There are the matrices that I just named here, and that's what you get. So there's a D-tran, just done pretty nicely, pretty good, okay? Now, when you get done with anything, I always say, check your work, okay? So make sure that, in fact, that D-tran works and gives you what it should get. The best way to first check it is that this thing multiplied by that thing should give you unit operator. They should be inverse of each other. Now, you know in quantum mechanics that I don't have a problem with this guy over here, or the inverse. If this is the matrix I think this would be the inverse of it. In quantum mechanics, all the transformations in normal quantum mechanics are unitary. And that means that all you have to do is transpose them, and if there's any complex numbers, they've got to be conjugated. Not so easy when you have 1, 2, 3, 4. But quantum mechanics has that advantage, that I don't really need to pull this trick. But this is the way a computer would do it most efficiently. So that's why I say in standard quantum mechanics, inverses are really easy, even if it's a big matrix. All right, it's time for physics. Time for some normal modes and stuff like that. So I'm going to tackle this one. And this is just a problem that you're going to be doing, except that the numbers are different. I have a very nice symmetry here. I've got K2 and K1 equal to 9. And then I have this little weaky spring in between here. Okay, so that's what we're dealing with here. And to get the secular equation, I need to know the determinant of this K matrix. Okay, 100 minus 1, 99 is the determinant. Okay, so we've got a secular equation with a 99 there. All right, and then you got a trace. The trace of this thing, I got 20. 10 plus 10 is 20, and it's minus the trace. So I put in minus 20 here. It's real easy to do these things. And then I factor, this happens to factor very nicely into 9 and 11. And at this point I have to say that we are solving a second order differential equation involving this matrix. So the eigenvalues are not frequencies. They're frequencies squared. Now we're going to fix that in a lecture on Monday, where we'll make a connection between these mechanical oscillators and two-level systems of quantum mechanics. But in that case, the eigenvalues will be frequencies. But for second order, this is what we've got. You've got to remember to square the eigenvalues to make this all work. Okay, so here's a projection operator for this thing. So this is telling us, after I get done putting in eigenvalue 2 to make projector 1, and then vice versa. Remember, these are products over everything except the dimension that you're interested in. And this is, I'm in all of them except 1. I've left 1 out, so here's what I get. And I get a very nice projector that's all 1s. That's clearly idempotent if I divide by 2. And then P2, well, that's involving all the eigenvalues except the second one. So I put the first one in. That's the 9 right there. I put in the second eigenvalue right there. Okay, pretty simple. All right. And then what I've got is an outer product of these two things. If I want to to factor this. This is the tricky part, factoring this thing into kit problem. And there's a nice way to do it with, you know, this is minus, why not make that minus? But I could have made that plus as long as I was consistent. So I can multiply this by any k1 and this by, divide by any k1, and I'm not going to change that. I'm not going to change the physics or the mathematics by doing that. But I'm not doing any gauge stuff here. No gauge. So the eigenvector, this is just a vector in the 45-degree direction, and this is the one in a minus 45-degree direction. So that's where our modes are going to be, and we already looked at a simulation that actually had that. So we'll look at it again, but with a little faster motion now. And so here we are. Get a chance to see what a beat looks like. And you got to also marvel at what we're going to be seeing here, which is a really pure form of resonance. It's one mass resonating the other one. And there'll be a period where this one is getting that one going. Come on, baby. Come on, baby. Come on. And then all of a sudden, the one that was giving it has died. It will die. And this will be the one that drives. It says, come on, come on. Come back from death. Come back. Be resurrected. Okay? And it will get this one. Now this one will be the driver. How do you tell? One of them will have a 90-degree phase this way, the other one will have a 90-degree phase the other way. Okay, so we'll see that. That's what's going on right in that picture there. But let's just look at the arithmetic real quick here. Okay, what we're saying is we've got a state vector now, general state vector. It's a linear combination of the eigenvector 1, which is 45-degree motion this way, and eigenvector 2, which is negative 45-degree motion. Okay, so that has an amplitude with an initial condition. I'm going to be setting the x0, 1 and 2 components, but this one is going to go at the frequency omega 1, whereas this one is going to go at the frequency omega 2. Well, not omega 1 and not omega 2, right? Omega 1 squared, right? And omega 2 squared. That's what we're dealing with right here. Okay? So I write omega, but I mean omega squared up here. That's what the k's are. But when it comes time to drive this thing, I'm going to use that frequency. Now, let's see, there's something else here that's important. And we're going to use this one for some real magic later on. This is the way you factor a sum of exponentials real quick, especially if they both have the same coefficient, that is, the same size. E to the IA, that could be this first one. E to the IB, that could be the second one. And I'm going to go E to the IA plus B over 2 times E to the IA minus B over 2. That gives me E to the IA. And then I just put a minus sign on that one. Now I get E to the IB sitting right there. So what I get then is a sum of exponential omega 1 minus omega 2 with a minus sign and then with a plus sign. That's a cosine. And then I see here the difference between those two quantities. That's a sine with a total minus sign on it. So let's go ahead and push this ahead. That's what it looks like right there. Okay. Now there's something else to notice here. But the main thing that I want you to notice is this little factor right here. This is the difference that gives a sign, but you got to divide by I, or multiply by I, is the way it looks like I've done here. So this has got a phase, a lag or lead, depending on how you look at it. Whether you look at one or you look at the other, this has got a phase of e to the pi over 2 I. So here's your magic pi over 2. Remember where the force had to be pi over 2 ahead to give energy or behind to take it, the maximally take it, maximally give it, right? That's a very important number, that pi over 2. And that's talking about pi over 2 with respect to coordinate motion. What we really should be talking about is velocity motion. We want them right on top of each other to be effective, right? You want the force and the velocity right in line. F dot V, you want to maximize that if you're going to transfer energy, right? So that's all going to be happening here in the simulation of this if it doesn't cause problems for us in the thing. So I'm going to go ahead and see if I can get it going on this screen over here. This is the guy right here. Now there's some other stuff in this animation that we're going to be talking about on Monday. This is the spin vector simulation. But what you're seeing is I started them off at 1 for this guy and 0 for the other, and I get beats. I get beautiful beats. And I emphasize that the beat frequency, okay, we're talking about omega 2 minus omega 1 over 2. It's a half difference. It means the period is twice as long. And you say, oh, what do you mean? The period's this long. There's a beat. That's what any engineer would say. But he's full of shit. This is half a beat. Half a beat. There's the other side of the beat over there. So it's that long. That's the period. It's twice as long as the engineer would call it. And half as fast. You're only getting one of these things half as much as he thought. So there's the beat. Cosine omega 2 minus omega 1 over 2. That's the envelope. The envelope goes there, and I've got to finish it to be kosher physicist. Okay? I'm not Jewish, but in physics you've got to be, because you're talking about bras and kets, and the idea is the operator is always on the left, right? The idea is that you read how things have happened by going from right to left. That's Hebrew. And most of the people who invented quantum mechanics are Jewish. And we're brought presumably Hebrew tradition, right? I don't know. I'm just making this up. But it's, you know, some way to remember what's going on here. Okay? So, while this thing is doing what I've shown here, if I go up here on the bunny slope, as they used to call it, the slope for beginners, okay, you get that frequency there, and then I go over here to this one, and I get this frequency, which is a lot faster. You can see that it's way faster than the one that's underneath it there. But the whole idea, and I'm going to go ahead and erase the paths and start off right on the axis here like we had before. I'll start right there. Bingo. And you can see, because the ellipse is tipped over, the thing takes off from the axis right away. Now there's some other numerology that's associated with this stuff that I probably ought to mention, because the computer will do it for you if you ask it nicely. So I'm going to go ahead on this one. And normally we would stop and show this, but we can show this after class. Now there's a problem. You see what happens is it skips a frame there. So it doesn't really show the beats, but it doesn't hurt to have a nice demonstration of that. I will just go ahead and run it real quickly here. Put the one on 0 and let the other one go from 3. It stopped. It stopped. It stopped. You see, it's back and forth very clearly, right? Now, what's neat about this demonstration is I can make the spring weaker. See how the spring practically disappears because it's out of focus? Okay, but it's also weaker because it doesn't have quite the lever arm, right? Now when I start this thing up, it's going to take a while before it completes the beat. I'll try to get that one right on 0 and let it go. Takes a while. See, it's pumping it up. And that's what we need to really look at. That's that pi over 2 that he was ahead. Now He's behind pi over 2. He came out the other side behind. Now we're back again to this one, right? So that's your pi over 2, first the one way and then the other. It's always pi over 2, but it's plus or minus. Okay, that's kind of neat. I mean, that's the thing that's good about these high symmetry oscillators. Okay. This is that simulation, I think, there. Now, what kind of figure do you get here? That's an interesting thing to work on. This figure right here, if you do a continued fraction expansion, this is all written out somewhere else. I'm not going to spend a lot of time on this right now. But if you count how many times this crosses this beginner slope, I count here 1, 2, 3, 4. That's 5. That's 6. That's 7, 8, 9, 10. Now, if I may have counted wrong, but let's compare. I think it's actually 11. Let's count this way: 1, 2, 3, 4, 5, 6, 7, 8. I must have missed
8 versus 10.
Yeah, this. Oh gosh, let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9. I was missing this guy in the middle. That's what the problem is. This looks like the axis, right? There's your 9 in this ratio right here, which is 1.22222. Okay, that's just what the ratio of the frequencies. Differences of the frequencies are what we've been working with. Also interesting are the ratios. Let me try counting again here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, that's a 9 to 11. All right. Okay. Well, we got to rush. We've got really 10 more minutes because we started 5 minutes late. That's what you get for coming in late, right? Bad. Here's the way you calculate those. For example, if you want to express pi in terms of fractions, you just keep doing this. This is little here, and that's what the computer has built into it. Okay, and it doesn't take very long before you're getting a number that really is very close to 3.1415926. It's not 6, it's 9 on this one, but you go another one, you get 3 more figures. So pi is really irrational, but it's beat by this, the golden ratio. Look at this. I'm nowhere near 1.618, and I've gone the same distance here. I'm still struggling with the first to second figure. Okay? So whenever I want people not to see a pattern, I set the numbers for golden ratio. So they won't ask about the pattern and spoil the talk I'm trying to do about the actual physics and the various motions, the raw motions. So immediately you get a mess looking like that. Okay? And nobody asks questions about a mess. Right? But when you have golden ratio, you're going to make a mess. You try pi or something like that, it quickly makes patterns that you see. And the patterns evolve. The patterns depend on what level of this. Unless it's a rational number, then this stops somewhere. That's the definition of rationality. Okay, enough of that. This is another diagram that we'll maybe go and talk about a little later, but what I'd like you to see, and I'm going to back out of this thing right here to get to it. What I'd like you to see is this a movie that I'm just going to make by clicking. I'm going to go forward. Oops, I should be going on this one. I'm going to go forward. Okay, back. Okay, I'm going to start, and basically what I'm doing here is I'm using this mode, which is in phase, and that's the one going in this direction, and this one, which is going in that direction, that's the one that's at minus 45, okay? And so I'm just leaving that one alone, and then the frequency difference between these two is what the beat frequency is. So I'm letting this one go tick, 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 while this goes tick, 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 tick. Leave that alone and add up the vectors on the second one as well as on the first mass, okay? So we start with the thing completely up, and then we go tick, okay? I'm sorry, we go, start here. Should have one that has it straight up, okay? Then the next tick is this, so this thing is ticked over here to 7 o'clock, that one's over there at 2 o'clock, okay? Add up those vectors, and you get this. Add up the vectors for the previous one, go back here. For this one, add up those vectors. Here, you're barely at 1 o'clock, okay? And this one is barely coming up maybe to 9:30 or something like that. Okay, so basically what we're looking through is we're almost to here. We are to this point on this graph. So this is time going down, okay? And what you're doing is you're having a beat. This thing is sending its stuff over, being 90 degrees ahead, and then finally creating a monster here, and now this one is 90 degrees ahead of that one. You see, and eventually it will come back to this. Now this is optics. This is polarization optics. What we're doing here is we're going from X polarization to left-handed circular polarization to Y polarization to right-handed circular polarization, then finally back to X polarization. So there's a typical semi-classical quantum dynamics that's the same mathematics as what we've been working with for the classical motion of masses. Well, we're going to finish with this one. This one is the one that's most like the problem that you're going to have to do, and that's going to have very little symmetry. 7 and 13 not equal, okay, for the spring constants, all right? Once again, trace and determinant determine a polynomial, which in this case comes out nice and even. If I'm a mean guy, I've given you one that doesn't. But in any case, this is the idea. And remember, squares of the frequencies, we get 4 and 16 here. And here are the eigenprojectors that go with that. And that's the fast one over there. There's the slow one there. Okay, and they're really different now, 4 and 16. Wow. Okay, so that's quite a difference. So this one shows you the initial projection. I'm doing a spectral decomposition, so to speak, here, writing the unit operator as P1 plus P2 times the very first vector, and then making outer products here that represent parts after I've projected them onto the eigenstate. And just looking at the eigenstate, this one right here, that becomes a coefficient minus 1/2, and this one square root of 3 over 2. So this is a typical example of how you would analyze the motion just with paper and pencil, so to speak. Anyway, this one has a really neat property, and that is that it gives a parabola. Now you used to think parabolas, that's what you get in sophomore physics with uniform gravity, right? This is anything but you get a parabola. You don't get the whole parabola like you do in sophomore physics. You can make a parabola arbitrarily big there. You just get this, and then it comes back on itself. Okay, now the question is whether we have the simulation to go with that, and that'll be the end of what we're going to do today. And it's all in honor of a very smart Russian mathematician physicist. And this is a guy born in 1821, it's a long time ago, in Boloshka something. He ends up in St. Petersburg. He dies on December 8, 1894. Chebyshev. And there's at least 7 spellings of Chebyshev. But this is a Chebyshev polynomial, and you're going to get another one in your homework. But it's really quite amazing, and I hope it will actually do it on the screen here. Yeah, there you go. It looks like a rubber ball bouncing back and forth. Isn't that cool? Now, if I just change initial conditions even slightly on this, then I'll go ahead and maybe do it on this one. I think this one will run for us. I'll go ahead and do that, and then I'll mess it up. Okay, there it is. Now I go up here and just start it a little bit off. Okay, maybe give it a little speed. Now it's going to make a Lissajous pattern. So in general, you're going to get sort of a figure eight like pattern. But that's cool, just right there. A parabola, right? In something that shouldn't have parabolas. Well, there's a lot of other things that you can make that way that are not parabolas, higher degree things. They're all called Chebyshev polynomials. And basically is one sine wave against another one, but with certain priorities. All right, I hope you've enjoyed a rather intensive lecture on something that I think you can use. We'll see you for some more of this story on Monday.